Well,
the eta will be omitted from the both side of the equation.
well, I mean, this equation, for instance, that one or that one, for instance, that we want to do that one, this one, okay, in principle, I haven't, oh my God, I haven't solved it here, but the way is eta minus delta t that multiplies 1 minus alpha. Eta is positive, alpha is positive, delta t is positive, so I can pass that, multiply that to the other side without altering the sign, smaller or equal than eta plus alpha delta t. I just operate in that and said alpha minus delta t plus alpha delta t smaller that eta plus alpha delta t. This cancel and the first one is eta, okay. And that also cancels, and then I have that minus delta t is smaller than 0. So since delta t is equivalent to delta t greater than 0, delta t is always greater than 0. Of course, because I've considered here, for doing that eta is always positive. Otherwise, I wouldn't have been able to multiply that. Okay. And the same for the other. Well, let's talk now about accuracy. Accuracy is the way, it's related to the way that the numerical integration scheme fits or reproduces the partial differential equation you want to solve. For instance, in that case, we want to solve this partial differential equation numerically. We want to integrate that. Okay? So we expect that any solution for any time, that when we replace the solution here, the solution we have obtained at a certain time, when we replace that, and we replace consistently at the same time this and that, we expect that in the limit, when delta t tends to 0, when I, with reducing the delta t tends to 0, that equation is exactly satisfied. So the limit, when I replace here the numerical integration solution, and I take the limit as delta t tends to 0, whatever is the scheme I've used, then that equation is exactly satisfied. If not, I don't have any expectation of getting the result. So if the limit solution doesn't fulfill the partial differential equation, what are the expectations of having any accuracy? That is called consistency. So at least the original differential equation has to be fulfilled in the limit of delta t tending to 0 exactly by the numerically integrated solution. But of course, I could also say, well, what is that not only the original differential equation, but also subsequent derivative with respect to time of the differential equations are fulfilled. So I just don't fulfill the, I just fulfill exactly the original, but also its first derivatives, the second derivatives, the third derivatives, and so on. The more, the better. Okay? Understand me? So, then, that is something which is a consistency, and that's something which is mandatory. If that's not fulfilled, just throw the scheme away. Okay? But then, if I just, the solution, I insist, taken to the limit as delta t tends to 0, the solution fulfills for every time step in the limit, not this equation, but also this equation, then I will say that I have second order accuracy. In the first case, it's a first order accuracy. First order accuracy is the minimum. Okay? That generally means that when I decrease the time step twice, the error is divided by 4. If I decrease time step 3, the error is divided by the square of 3, etc. That just says that it can be proven that this also indicates that the error is, so to speak, in the limit, proportional, close to the limit, proportional to the delta t. If I just take 1/2 delta t, then I reduce the error 1/2. Okay? That is this, so that's much better than this. If I get a scheme which is second order accurate, then I can expect that with large time steps, I would have much more accuracy. So I will need less time steps to get the same accuracy. So that's the concept of accuracy. Nothing to do with stability. Stability is related to propagation of errors. Accuracy is the way in which the exact solution is recovered in the limit. And indirectly, the way that the not in the limit solution for finite delta t, I am approaching the exact solution, the analytical solution. Okay, understood? So let's see what in this problem, what kind of accuracy do I have? And this is a typical stability analysis. They are very simple analysis. Of course, they are more complex when you look for complex problems, but the spirit is the same. Okay, we are using alpha method. So that's our scheme. If you had to use another scheme, there are many other schemes for integration partial differential equations. Maybe you could have used, Runge-Kutta, for instance, or some other examples. They all have different properties. But now we are focusing our analysis in alpha method. In alpha method, we just did this interpolation, I recall, the interpolation of R, that was the basis of the method, in this way. So, in other words, Rn plus alpha depends on tau n plus 1. So that the solution at Rn plus alpha, maybe going back to this equation here, depends on how far is taking this time. If the time, if now I have these results are already done. And now the point is, okay, when I increase delta t, for instance, or when Tn plus 1 is taken far away from that, so how are the errors that they commit in Rn plus 1? That's what I want to evaluate, okay? So what I want to specify with that is that in this scheme, what is the play of the time, displaying the role of time is Tn plus 1. Tn plus 1, according to that, Rn plus alpha doesn't depend on this term here, Rn, because Rn is given. It will depend on how big is Tn plus 1. So in that sense, I can consider that Rn plus alpha in that equation is a function of Tn plus 1. That's just what I want to say. Okay? So the greater is Tn plus 1, or if I change Tn plus 1, then this will change. Okay? How do I change Tn plus 1? Typically changing the delta t. Okay? Okay, so now let's take, if this is a function of t through Tn plus 1, let's take the first derivative with respect to Tn plus 1. So when I take the first derivative, look, this doesn't depend on Tn plus 1, and this depends on Tn plus 1. So r dot n plus alpha is the derivative of this with respect to n plus 1, which is alpha times the derivative of this with respect to a Tn plus 1. So I can say that r dot n plus alpha is alpha times r dot n plus 1. Just simple mathematical derivation. Okay. The same for tau. I do the same interpolation for tau. So tau is again a function of n plus 1 in the sense that this is fixed, and that is going to change as I change n plus 1, which is inside here. So again, the derivative of tau with respect to t controlled by Tn plus 1, is alpha times tau dot n plus 1. So finally the results that I get is that Rn plus alpha and is equal, the time derivative of Rn plus alpha is alpha times the time derivative of Rn plus 1, and tau dot n plus alpha is alpha tau dot n plus 1. And if I now take a second differentiation, for instance, I could go to the infinity for that, but now, of course, r dot n plus alpha is a function of r of t through this derivative, because Rn plus 1 depends on Tn plus 1, and r dot n plus 1 depends on Tn plus 1. So, the second derivative will be alpha as a constant times the second derivative of that. So finally, I can conclude that r dot n plus alpha is alpha r dot n plus 1, and r double dot n plus alpha, the second derivative of r with respect to n plus alpha with respect to time, is alpha times the second derivative of r with respect to n plus 1. These are just algebraic operations, okay? So now, let's consider that equation and that equation. And consider that equation applied to the time step, the time step tn plus 1, and integrated at time n plus alpha using the alpha method I did. Okay, so this is the alpha method I used. At the left-hand side, I have just the slope. At the left-hand side, I have the evaluation of the function. I'm just considering the loading case, because otherwise it's 0. There's no problem. So I consider that. And look, again, Rn plus 1, that multiplies, sorry, how is it? Rn plus 1 is Rn plus delta t over omega that multiplies that. And then, I think that this had to be removed here. This is not correct here. So Rn plus 1 from this equation is Rn plus the increment of time, which is Tn plus 1 minus Tn divided by eta, times tau n plus alpha, that depends on Tn plus 1 minus Tn, and so on. So, finally, I can take the derivative of R here with respect to T. Where is T here? T is Tn plus 1. Where is it? It's here and in here. This should be dropped too, okay? So T is in here, and here Tn plus 1 is in here. So if I'm going to derivative, to differentiate Rn plus 1 with respect to T, look, that derivative is, first, differentiation with this time is just 1 over 8 eta times this term, okay? Plus differentiation with respect to this time, with this term, Tn plus 1 minus Tn divided by eta, times dot minus R dot, which I have proven it is alpha time tau dot and alpha R dot. So finally, I can obtain with this derivation what is the time derivative of R with respect to T at n plus 1 in this way. And now we can take the derivative of this in turn. Second derivative of T. Where is T here? T is T, the time for the second derivation, differentiation is in here and in every one of those. So by doing this differentiation, I think by differentiation of that, I obtain a term which is delta T over eta, 1 over eta, delta T is that, differentiated with respect to that, is 1 over eta, times all these terms here, okay. And now I have to differentiate with respect to this term here. So this is 1 over eta times the differentiation of that, plus 1 over eta times the differentiation of that. So, after collecting terms, the single formula, again considering that the second derivative of tau and the second derivative of r at n plus alpha is alpha times the second derivative of tau and r and n plus 1. That's the formulas that I obtained before. We have them here, okay? Just a single algebraic operation. I'm not going into details, but most probably you can do it at home on your own. Finally, we obtain an expression that says how is the second derivative of r provided by the numerical integration method in terms of some derivatives at these entities here, okay? Okay, now, if I have the first and the second derivative of r, I am able to replace them here and here and see how these equations are fulfilled, okay? So by replacing at time tn plus 1, this first derivative, and here the values at time n plus alpha, then I can check this equation should be fulfilled. Otherwise, but to be fulfilled when delta t tends to 0 in the limit. If otherwise, we say we don't have any consistency and we cannot expect anything from the integration. And then can also try, since I have the second derivative, can also try this one. And I can go further and further, okay, and check the third derivative and so on. That's by doing that. So that let's see what happens. First one, let's check this one. By checking this one, the first one, I just replace r dot in plus 1. Here I place the differentiations that I had here, these equations I have here, okay? And then I obtain this expression, okay? What happens with this expression when delta t tends to 0? What happens? This term drops. And what do I obtain? R dot n plus 1 equal 1 over eta, tau n plus 1 minus r n plus 1. By the way, it's function. Okay? When delta t tends 0, the values that I've numerically obtained at time n plus 1, which is any time, because this is a general time, is fulfilling that equation. So there is consistency. Disregard the value of alpha, of eta, and whatever. So there is always consistency. Okay? So I can rest, so to speak. I can breathe deeply because my integration is going to be consistent. If I want more accuracy, I've just to diminish my time step and I will get more accuracy. Okay? But I will always, in the limit, I'm just converging as delta t tends to 0 to the solution, to the analytical solution. But can I go further? Is the numerical method able to go further? Let's look. Let's now replace the second equation I've obtained here. Okay, let's consider the second equation. And then let's consider the point that delta t, when delta t tends to 0, this term drops. So what is fulfilled is that equation. R2 equal 2 alpha over eta that multiplies tau dot, R double dot is 2 alpha over eta that multiplies tau dot minus r dot. And let's compare that with an analytical second order equation. What's happening here? Let's compare that with that. Is it always, this one always replicates that one, excepting for alpha 1/2. So I just find out that if I take alpha 1/2, the numerical integration solution in the limit not only fits the original differential equation, but also its derivative. So I don't have not only have linear convergence, but also have quadratic convergence. And that is something that can be checked. So you will be requested in your assignment to just do experiments to see that when you use alpha equal 1/2, by using the same time steps, for instance, and comparing alpha equal 1/2 or alpha equal 1, you are more accurate using the alpha equal 1/2 than alpha equal 1, which should be expected from this accuracy analysis. Of course, there is no sense, it can be proven, that for subsequent orders of approximation, there is no conditions. Not. So just this method only fits the first and the second derivatives. There are other methods that fit more than that, but they are more complex and so on. And this is enough for our purposes. Okay? Just for introducing you the issue, the accuracy is obtained with certain values of the alpha. So the summary is the following. You can use any alpha between 0 and 1, and the method will be consistent. So you can expect, as delta t tends to 0, converge to the analytic solution of the partial differential equation, so to the analytic solution of the problem. Then, however, when alpha belongs to the interval 1/2, 1, so when alpha is greater than 1/2, and of course smaller than 1, then that convergence is, or the integration is unconditionally unstable. So no matter how is the time step, you just have some solutions with some error, some lack of accuracy, but you won't have explosions. The errors will not be transmitted from one time step to the other. Okay? You will be requested to do that. You will be requested to try alpha equals 0 alpha equal 1/2, alpha equal 1, with large time steps. And we'll see that you will able, with that in this range, alpha in this range, you will obtain solutions that, okay, they will be different from each other and of course diverging or converging, but you will never have explosions. But as alpha is smaller than 1/2, if you have small enough time steps, you have large enough time steps, you have explosions. You cannot get any solution. That's the consequence of stability. And then, specifically, for the specific value, only 1, alpha equal 1/2, you have more accuracy because you have quadratic convergence instead of the regular linear convergence. Okay? So these are typical things that probably is the first time you are facing, and in the assignment you are requested to experience on yourself, okay, on your own, and then take appropriate consideration so that this stays forever in your minds. Okay, so how is it the time? Let me check.